Okay, let's dive right in. Today, we're going to get into three of the biggest ideas in physics: work, energy, and power. We'll start by untangling how work and energy are connected, because that's really the heart of understanding how anything moves, stores up power, and then unleashes it.
But first, let me throw a little puzzle at you. Think about this. You're pushing against the solid brick wall with everything you've got. You're sweating, your muscles are burning. You feel like you've done a ton of work, right? Well, guess what? In the world of physics, you've done absolutely zero work. How on earth is that possible? Well, stick around because we're about to figure it out.
So, to solve that little mystery, we have to start with what work actually means to a physicist because, it's a little bit different from how we use the word every day.
Okay, so here's the key. In physics, for work to actually happen, two things are non-negotiable. You have to apply a force, and the object has to move because of that force. So when you were pushing on that wall, yeah, you applied plenty of force, but the wall didn't budge. No movement, or what scientists call displacement, means scientifically speaking, no work was done. And the math behind it is actually pretty straightforward. The formula is just work equals force times displacement. And displacement is just the fancy term for the distance the object actually moves. So it's a really direct relationship. The more force you use, or the farther you move the object, the more work you've officially done.
But believe it or not all work is created equal. When the force you apply actually helps the object move, like when you're pushing a box across the floor, we call that positive work. But what about something like friction, which is always fighting against you? Well, since it opposes the movement, it's actually doing negative work. And then, of course, there's the strange case of zero work, even when things are moving.
And that brings us right back to zero work. So our first example is the wall, right? Lots of force, zero motion, so zero work. But the second example here is a little more subtle. Imagine you're just carrying a heavy box across a room at a steady pace. The force you're using to hold it up is pointing up, but you're moving forward. Because the force isn't in the same direction as the motion, scientifically, you're not doing any work on the box. Crazy, right?
Okay, so what happens when you do manage to do some positive work on an object? Where does all that effort you put in actually go? Well, it gets transferred to the object, and it becomes energy. Specifically, it becomes the energy of movement, which has a special name: kinetic energy.
And it is as simple as it sounds. If something is moving, it has kinetic energy. A car flying down the highway, a planet zipping around the sun, even just you walking to the kitchen, it's all kinetic energy in action.
Now, the formula for this is 1/2 times the mass times the velocity squared. And what this is telling us is that an object's kinetic energy really depends on two things: how heavy it is, that's the mass, and how fast it's going, that's its velocity. But you've got to notice that the velocity part is squared, and trust me, that is a huge deal.
Here's why that little squared v is so incredibly important. If you double an object's speed, you don't just get double the energy. No, you actually get 4 times the energy. This is exactly why a car crash at 60 miles per hour is so much more destructive than one at 30. That energy goes up like crazy with speed.
And this principle is universal. It applies across a massive range of scales. From the unbelievable energy of a meteor burning up in our atmosphere to the simple act of throwing a ball, the rule is always the same. If it has mass and it's in motion, it has kinetic energy.
Okay, so that's the energy of things that are moving. But what about energy that's not in motion? Well, that brings us to the other side of the coin: potential energy. It's all about stored power.
The best way to think about potential energy is as energy that's just on standby. It's saved up inside an object just because of its position, like how high it is, or its shape, like a stretched out rubber band. It's just waiting for the right moment to be let loose.
So, one of the most common types you'll see is gravitational potential energy. The formula is just mass times g, which is the acceleration due to gravity, times its height, h. All that means is the heavier an object is, or the higher up you lift it, the more potential energy you're packing into it. And here's a perfect everyday example of that. A book just sitting on a high shelf has way more stored energy than the exact same book on a lower shelf. And it's purely because of its position. It has more potential to fall and release all that stored up energy. Now, for the really cool part, these two kinds of energy, potential and kinetic, they aren't separate things. They are in a constant state of exchange. They're like two sides of the same coin, and they're always flipping, transforming from one to the other.
So let's just break down the difference one more time. Kinetic energy is active. It's the energy of doing something, like a moving car. Potential energy is stored.
It's the energy of waiting, like the water held back by a giant dam. But the most important thing to get is that one can become the other, just like that.
And what's the ultimate example of this? A roller coaster, of course. You know that slow clack, clack, clack as the cars get pulled up that first massive hill? What's happening is you're just building up a huge amount of gravitational potential energy. At the very peak, that one moment before the drop, your potential energy is at its absolute maximum for the entire ride.
And then you finally go over the edge. As that coaster plummets downwards, all of that stored potential energy is rapidly being cashed in for kinetic energy. You're losing height, but you're gaining incredible speed. That thrilling rush you feel in your stomach? That is literally the feeling of energy transformation.
And this isn't just for roller coasters, you know. Think about an archer pulling back a bowstring. They are loading it up with elastic potential energy. The second they let go, all that stored energy is transferred to the arrow, which flies off with a ton of kinetic energy. It's the same beautiful exchange.
Now, this whole constant conversion, this dance between potential and kinetic, is all governed by one of the most fundamental laws in the entire universe. It's a rule that, as far as we know, has never, ever been broken.
And that rule is the law of conservation of energy. In any closed system, the total amount of energy is constant. It can change from potential to kinetic, from chemical to heat, but the grand total never, ever changes. You can't create new energy from nothing, and you can't make it just vanish into thin air.
Let's go back to our roller coaster one last time. If we could ignore things like friction for just a second, the total mechanical energy, that's the potential plus the kinetic, would stay the exact same at every single point on that track. As the potential energy goes down, the kinetic energy goes up by the exact same amount, and then back again. The books always balance.
Which of course brings us to one final nagging question. If energy is always conserved, if it's never really lost, then why does a bouncing ball eventually stop bouncing? The energy doesn't just disappear. So where does it go? Well, the answer involves forces like friction and air resistance, which take all that nice, ordered motion and convert it into other, messier forms of energy, like heat and sound. But that's a puzzle for another